Hi, good morning, good afternoon, and good evening, everyone, depending on where you join us from today. I hope you're all feeling awesome because we feel awesome as we got the honor to introduce us, I think maybe one of the best speakers in AI, who is Seth Juarez. Hi, Seth, how are you today?
Fantastic. Excited to be here.
I'm excited also to hear you talking about machine learning today.
That is correct. I'm super excited. We're going to get into it today.
Yes, it's
And
going to be awesome.
and is it so that this is the first part in a two-part session?
That is
Okay.
correct. We're going to motivate some things from first principles based upon some of the earlier learnings that you've all have had in the math sections to figure out like how this stuff actually works. And then in the next one, we're going to get into some deep learning frameworks, particularly PyTorch, and how to get those to do some pretty cool stuff.
That sounds really exciting. And I think before getting into the session, it is also important to mention that Seth is joining us from very far away, actually. And it's very early there, right?
It's not too early. It's 8 o'clock in the morning. I live in northwestern United States in a state called Washington, and so it's it's the state closest to Canada, all the way on the west coast. It's pretty cool.
That's pretty cool, exactly. All right, so before we get to your session, we would like to have a few words about what is AI 42. Would that be fine?
Awesome. I think that's great.
Great. Let's So welcome everyone to the next session of AI 42. For those who just joined us for the first time, Håkan, could you give us an overview of what is the motivation of AI 42?
Yeah, sure, Eve. So the idea here behind AI42 is we would like to give everyone a chance to get into this interesting field of machine learning and data science. So the way that we've done is we've invited recognized speakers and industry experts. So they will have sessions that we're streaming to YouTube, to Facebook, and to Twitch 2 times a month on Wednesdays at 5 o'clock. And what we have done is we wanted to start with the basics. So we started out with mathematics, with statistics, and with probability theory. And after that, we've moved into languages like Python and R. And we've also looked at tools like we'll be looking at Databricks and Power BI and see how can you actually set up your own machine learning pipeline. And we will also have a look at more advanced topics like reinforcement learning and explainable AI. And in addition to these more theoretical topics, we also will have some more practical workshop sessions where you can put this theory into practice.
Yes, and if you want to hear more about us, you can follow us on Instagram, Twitter, or Facebook. And if you would like to see the previous sessions we had, you can just follow the link to our YouTube channel. And if you want to see our upcoming sessions, you can just scan the QR code for the meetup group we have.
Yes, and we would also like to thank our sponsors. So we're sponsored by Microsoft and we're sponsored by Miles.
And we also would like to say a big thank you to our supporters, for example, like Global AI Community, C# Corner, and Mina Murray, who composed our music for our streams as well, and Levi, who made our graphics for the streams, for the speaker cards, and so on. So thank you a lot.
Yep. So shall we get back to Seth?
Before that, I would like to mention that maybe you would be interested in other AI-related sessions. And for that, you only need to register to Global AI Virtual Tour and check out what kind of sessions are coming up. It is going to be like a 48 hours live stream with more than 30 awesome speakers from all around the world who are going to share their knowledge in the field of artificial intelligence. And with that, I think let's go back to our speakers today. So welcome back, everyone. And hi, Seth. I hope you are prepared and ready to go.
I am ready. Now, I'm going to go kind of fast. And so if anyone has any questions, just pop them in the chat. I'm looking. If I side glance, I'm side of the eye looking at your questions because we're going to go through a lot today. I'm pretty excited.
We are also very excited. And yes, remember to put your questions in the chat. And I think we can just give the stage to you, Seth.
Let's do it. I'm excited. If we can share my screen, that would be fantastic.
Yes.
Yes, we'll do that.
So smoky. That's so cool. I'm going to get my sound effects ready because I'll play them every once in a while. All right, we're getting started with machine learning. And the reality is that sometimes machine learning has a bad rap, you know, like AI and stuff. Like tremendous obscenities have been done with AI in the films, in technology. You know what I'm saying? So today we're going to talk about what machine learning actually is, and then we're going to motivate a really dumb problem that you should never use machine learning with, but we're going to do it anyways because I want to make sure that we understand what's happening at its rudiments. We're not going to use any deep learning framework. We're just going to do some examples with just like regular Python, right? And I'm pretty excited about that. So what is this whole thing anyways? Because people talk about AI, they talk about machine learning, they talk about deep learning, and sometimes it gets a little confuserating. So let's start with artificial intelligence. Pretend it's a huge bubble. I shouldn't say bubble in the tech community, but pretend it's a bubble, right? When it comes to artificial intelligence, it's actually a really big field. And the thing about it is that it's quite old. And when I say old, I mean like old as in 1950s old. And there's a lot of artificial intelligence that's happened for a long time. So, for example, writing code to play tic-tac-toe against a computer is actually not hard, right? You've also seen AI that tells you where to go. But that's not quite the same as machine learning. And let's make a little distinction. So, for example, your AI to help you play chess. For some reason, we know this is AI, but we also have a feeling that it's not machine learning, right? Because it turns out there's this branch of artificial intelligence that you could term as glorified search. Oops, I always do that. Search, right? So there's things like adversarial search. If you've ever heard of Minimax, it's an adversarial search algorithm that makes you play things like chess or tic-tac-toe. There's other ones that help you find things like A star. So if you're ever on an app that tells you which way to go, sometimes you know how it reroutes you because of traffic. It's using AI, but that's not quite machine learning. It's not the same thing. So let's talk about machine learning, right? Because the difference between this one and this one is that you can actually search the space and you can actually define the space. But with machine learning, and this is interesting, what if you can't define the space? Like you're looking at a picture. How do you search for all pictures and then say, oh yeah, that's a dog? It's literally impossible to do that. And so there's certain class of algorithms where you give it data and it produces algorithms for you. We'll get into this a little bit more. But you probably heard of a ton of machine learning algorithms that do that, like for example, decision trees. You've also heard maybe of support vector machines or something called logistic regression or even logistic regression or even just regression. You've heard of these before, or maybe something like neural networks. These are all algorithms in the machine learning class. But now you've also heard of something called deep learning. This is the inner bubble of all of them. And the reality is that deep learning is like neural networks plus. That's what neural networks are. The reality is for it to become deep learning, the depth of your neural networks, the depth of your neural networks to make it deep learning, that really depends on your marketing team. These are the jokes, people. But yeah, so neural networks that are really deep, those are deep learning. And we're going to get into that next time. with PyTorch. And so this is a good way of understanding all three areas of artificial intelligence, because artificial intelligence is quite large. There's a ton of other things that have happened in the 90s. It's really big. But then once you understand these things, the difference, it really helps a lot. Okay, so machine learning is basically finding and exploiting patterns in data. We're replacing the idea of us writing code with giving data, and it figures it out. And the most central thing is generalization. And here's a really, this is how I like to think about it. Machine learning is a process of converting data into functionality, and always starts with a sharp question. Now, there's a machine learning can answer a bunch of questions, but as we're getting started, there's 5 that you should think about that are pretty well trodden. Like, for example, how much or how many? Given a set of data, can you predict how much or how many will happen? So, for example, stock price. Or another one, which class does this belong to? Say you're giving a picture and you want it to know, like, is it a dog or a cat? That's a class. Are there different groups? Which does it belong to? Or is it weird? Which option should I choose? And these all have very fancy computer sciencey things. Like, for example, this one is called regression. This one's called classification. This is clustering, anomaly detection, and recommendation. And they belong to 2 distinct classes of machine learning. One is called supervised learning, where you give it the data, but the data includes the data plus the answer, and then it does a thing. And I'll get into more specifically what that is. We're gonna live in this area. We're gonna live in this area right for this session, because there's really, I mean, you can go into the other ones as well, but we're just not going to at the moment, because I want to motivate what we do the next time. But these other ones are called unsupervised learning, right? Then there's this other category, because I don't want the pedantics out there to be like, this is not all of it. No, there's others. Like, for example, there's something called semi-supervised learning, right? There's something called self-supervised learning, right? There's also other structural types of machine learning, like probabilistic graphical models that let you do other things. So there is a bunch of other things. There's also, for example, something called reinforcement learning. We don't have time to get into all of the, oops, no, I don't want to end the show. Reinforcement learning. We don't have time to get man, I'm terrible at writing. Reinforcement learning. We don't have time to get into all of them, but if they invite me back, we can dive into any of these. So we're going to live in this area for today, if that's okay, just to be specific. So let's get into this notion of classification and supervised learning. Generally, when we're writing code, we think like this. We're like, we got to make an algorithm here such that when we give it input, the answer comes out. That's programming. It's like, yeah, I'm using a Wacom tablet. It always messes me up. It's really funny. So this is how we think. We think of like, okay, I need to give an answer. How do I break it down and create a series of steps to solve the problem? But it turns out that there are certain classes of problems that are just really hard. Like, for example, if I have a picture of a cat, right? This is my cat. Wow, that's so good at drawing. And you have a picture of a dog. Here's a dog. This is a terrible dog, but you get it. How do you search that? I mean, like, you can imagine creating an algorithm where you're like, okay, well, if I look at pixels here, right, and I look at pixels here, but think of like the for loops and the if statements that you're writing. This isn't code that you want to write because there's no algorithm that can create the right answer. And this is a problem. Right. And thank you, Stephen, for the Wacom tablet curse. It's really nice, except when it isn't. So the idea is that when it comes to certain classes of problems, these are so hard that it's almost better if we could magically flip this And that's what supervised machine learning does. Instead of creating of thinking about an algorithm, we give it the answers and the input, and an algorithm comes out. And you're thinking, what? How does it do that? And that's what we're here to talk about. But these things have very specific. There's specific nomenclature in machine learning for this. And this half here, I know I keep this half here and this half here have some names, and those names are obviously data. And whenever you hear of a machine learning model, think of it as a fancy way of saying algorithm that was learned and not written. That's what a machine learning model is. And I'll show you. We're going to make a really dumb one, and you're going to be like, "Oh." But you're going to see that even though it's not going to be super, you're going to see that there's going to be a super satisfying ending, but you're going to think the problem is dumb. We're going to use the exact same techniques on bigger problems, and it's going to work still. And that's the surprising bit, that it actually works. So the question is really what happens in here, and that's what we're all about today. But the reality is, once you do this, putting this in production is just like we had before with our old code model. Is that, remember, we used to have an algorithm and then stuff and then the answers? That's what we do. We just plug in the model, and that's what happened. Now, there are various commercial offerings out there where basically you're renting models. That's cool. Just like a data grid, you don't want to write that from scratch. Or maybe you do because you like that sort of thing, which is great. But sometimes you just want to use models, and there are techniques for using them. Sometimes you just want to make models better, and there's ways to do that too. And sometimes you want to make models from scratch, and that's what we're going to do. But we're going to work on a really, really, really dumb problem. Really dumb problem. Put that out of your head, but I want you to actually see in your head and understand exactly what's happening inside of these things, which I think is good. So high school teachers would be offended with this approach. Wacom tablets. I know. I love drawing on these things, though. It makes me feel like I'm doing something. All right. So here's the problem. Okay. A silly example. So you know that I know TM, a silly example. What we're going to do is we're going to work on pictures that only have 9 pixels. This is our machine learning problem. And what we want to do is we want to make a machine learning model that can predict whether it's darker at the top or darker at the top or darker at the bottom. That's what we want to do. So for example, this one right here, for sure, darker at the top. So the answer is top. Let's go. Let's see if I can find one that's darker at the bottom. I think this one right here. No, it's not. It's not. This one right here. This one would be darker. Why does it do that? This would be darker at the bottom. Right? That's what we want to do. We want to make a machine learning algorithm such that we can predict whether it's darker at the top and darker at the bottom. So basically, we want to make a function. We want it to invent a function such that when we give it our picture, right, it says top or bottom. Does that make sense? So let's start first with what does the X look like for us? Well, it's actually quite simple. For us, right, these are the X's. This is all the pixel value. So so for us, X is this picture that has these 9 squares in it, and they're very dark. But in real computer speak, they're basically just a bunch of numbers. If you think about it, really, that's all it is. And for those of you that want to be super pedantic, I know that the higher the number, the lighter the color, but we're just doing the reverse, right? So this is the X. Remember, we have to give it the input and then the answer. The answer is here. Y. Now, I cheated. It says 1 and 0, but I'm going to change the zeros to -1s later. Just remember that. It just makes it nicer mathematically. But still, you have a way of knowing y. If y is 1, it's darker at the top. If y is 0, it's darker at the bottom. So now remember how we had our little square where we gave it the answer. We gave it the answer, and then we gave it the input. Basically, X is this input right here. You can see that. And then Y is the answer right here. And what we want to do is we want to produce some function, or what we call model. Okay, so far so good, right? Good. Now the real weirdness starts with, well, what the heck does that look like? This is like a serious question. Now, by the way, please stop me, because all of a sudden it's going to get like super crazy and you're going to be like, what's going on? So just stop me. I want to slow down if anything's ever going on. But basically, remember, the machine learning, supervised learning problem is we give it the answer, which is going to be like 1 or -1 or 1, 1, 1 or 0 or -1. And then X is the input, which is basically this vector. Now, hopefully those of you that are here have gone to the previous sections, because I'm gonna start talking about it in a mathy way. But if some of these mathy talk things are weird, just let me know. Because in the United States, we have math. Everywhere else, they have maths. Because y'all have extra in Europe that we don't know about, I guess. All right, so what does this look like? So stay with me for a second. I'm going to make something up that's going to seem completely dumb, but I think it's going to work. So pretend for a second I set up this structure here. And these are the numbers. Each one of these things are the values of how much the pixels. So 3, you know, this is 9, 128, 52, 32, 251, 128. So here are the pixels, right? These are the pixels. So 25. These are each of a hello from Asia, Stephen. Wonderful. So these are the pixels that are coming in, the values. Now, what I want us to do, and we're going to do this as an exercise in our brains, is I want us to pick numbers just at random, such that for each of these W's, when we multiply these numbers together, we're going to get a new value. So let's just say we're going to get W1 times 255, right? And then we'll do W2 times 3. And this will be 9 times W3, right? And 128 W4, 52 W5. You see that? So that's what we're doing. So we're going to multiply these W's. I want you to pick them. And then what we're going to do is we're going to add them all together, and then some answer is going to come out. Just like a single answer, right? I want you to pick W's such that when we multiply these things together and we add them, this number will tell us whether it's darker at the top or darker at the bottom. Now, what numbers would you pick? I feel like I need to put some. What numbers would you pick? Now, if you could put in the chat, just write it in, because I think that inspiration always requires perspiration, and so just write it in. What numbers would you put for W's, such that here I'll put the mysterious strings on, such that when you multiply each of these x values by this number and add them up, what would it be? Now, I'll give you a hint. Remember, we're trying to do top or bottom. So this middle area we don't care about. So let's just make all of these zeros. Right? Let's make them all zeros. All of them. Now notice that when we multiply these numbers, they add no significant value at all. Now, this is like, when you think about it, it makes perfect sense. Let's add ones right here for all of these. So these are all ones. All ones. So basically, these things are just getting added together. We're basically adding the top pixels. We're just adding them all together. Right? Okay. So we'll leave that there. This part disappeared. Now what we're going to do is we're going to add minus ones here. So basically, if you factor out the minus ones, right? So we'll do -1 times adding up all of these pixels, right? Like, if you factor out the -1, then it's just ones left, and you're basically adding all these pixels and multiplying by a -1. So now at the top, there's the top pixels right here, right? That are added together. And then at the top, there's the bottom pixels, right? That are added together and then multiplied by a -1. So if this is stronger, when you add these two together, if the negative is stronger, the answer will come out negative. If the positive side is stronger, then this will come out positive. And so all we need to do is see, is the answer positive or negative? And we know whether it's darker at the top or darker at the bottom. That easy. So if I was in person, I'd be like, hey, any questions? And it would be a trick question because you're probably wondering, well, what is this B doing here hanging out? Well, this thing, like if you add a big negative number like -200, this would force it to always guess negative. Or let's just say you wanted to predict whether it was slightly darker at the top within a certain margin of the bottom and you still guess top. This number here, when you add it in, will basically influence it towards the negative side or towards the positive side. Yeah. This thing is basically a bias that biases it towards the negative or the positive side. Now, if you're looking at this from a linear algebra perspective, this becomes a vector, this W, such that when you take the dot product, which is what this is, think about it, between these two things, it will tell you the number will be either positive or negative. And if you're looking at a geometrical linear algebra, basically a vector is like this line in space. But when you take the dot product between it, basically it's looking at everything that dot products with this vector, where it's 0 creates a plane in 3D space, right? And when you take a dot product of it, if it's on one side, it's positive. If it's on the other, it's negative. And so that's just a geometrical analysis of this particular operation, because this is the dot product plus a bias, which is this number right here. So let's test it out. Let's test it. Everyone okay so far? By the way, if you're not okay, this is okay. This is like years of grad school for me, looking at this stuff for a long time. So if it doesn't make sense, it's my fault, not yours. So let's try it out. So here is an actual 9 square thingy. 9 square thingy. Clearly it's darker at the top. So let's put in our numbers, ones and -1s. Go back. Notice that the answer is down here is positive. And so we guess darker at the top, which indeed it is. Let's do the other thing. All right. We multiply it by our magic numbers, and then out comes a -234, which means it's darker at the bottom. Done. Easy, right? So I'm giving away stuff now because you're gonna be like, well, this is dumb. Yes, it's very dumb. But this is actually machine learning, a machine learning classifier, right? This W and this B is the model. And positive or negative is the prediction. I'm not kidding. This W that it learned, which is, remember, for us, it's 1, 1, 1, 0, 0, 0, and then 0, and then -1, -1, -1. This is the model, right? Because B for us is 0 because we didn't need a bias. This W is the machine learning model to predict whether it's darker at the top or darker at the bottom. I feel like I need to. You're thinking to yourself, surely it's more than this. No. It just becomes more complicated the more layers you add, and we'll talk about layers. W is that's a really good question. So the thing is W a function? Yes. It turns out that any vector or matrix is a linear function when you multiply it. So for example, for us, h of x basically becomes this function where we pass an x and we get w dotted with x. This is our function. So h of x, let's do it in lambda notation. That's it. That's our h for this problem. Yeah. And if you think of a matrix, it's basically a linear transform or a fine transformation between two vector spaces. And so it's really this simple. When we go into the stuff next time, you'll see that these functions become more complex, because the reality is that this, sorry, I put h there, but it should have been w. Apologies. This basically, if you think about it in real space, becomes like a line. Remember, y equals mx plus b, but we're doing it in vector space, which means that there's more dimensions, and that's it. So the question is, look, we had to brain invent our w's and our b. The question becomes, how do we get these w's and b's? That's a great question. So what we're going to do is we're going to make another thing that helps us find the best w's and b's. We want to find a way to minimize the amount of mistakes that we make when creating these w's and b's. And again, when you look at this little handy dandy word, you start to think of calculus, because calculus is fantastic at minimizing things. And so what we're going to do is we're going to invent a new function that tells us how bad we are at this. And we're going to use calculus to minimize that thing. So hang with me for a second. I'm going to show you a function that's not super complicated. All right, this is a function. You can see there's an L where we have this function, the one that we're using to predict, and the actual answer. Because remember, we haven't used the answer so far. So think of this one. This is a function such that, pretend for a second we guess top, right? We guess top, and the answer is top. Now, in reality, this is going to be a number like 1, or bottom, right? This could be -1, bottom -1, right? So if we guess correctly, when we subtract these two things, we get 0, and then we square it, still 0. Boom. Okay, this one, if we guess negative, -1 minus a -1 is 0, and then we square it. Good. Now, if we guess top and the answer is bottom, right, we'll get a -1 here and a +1 here. 1 minus a -1 is 2 squared. We get 4. Do you see that? If it's bottom, if we guess bottom and the actual answer is top, right, this is going to be -1. This is going to be 1, right? So we're going to get a -1 minus 1, which is -2 squared, gives us 4. So anytime we make a mistake, we get a positive answer. Anytime we get it right, we get 0. So there's another question. Is finding W determined by which algorithm we use? Yes. Again, we'll get to more of this next time, but just stay with me on this W, because what's going to happen is when we do it at a larger scale, there's going to be a lot of W's, and there's going to be other things interspersed in between with deep learning. But it all comes down to W's and B's that are arranged in different ways with functions in between them. Okay, so this function here is called a loss or cost function. It measures how bad we are, how bad our predictive function is with respect to the right answer. Now, remember, for us, it's this, right? our loss function is this. So we back plug this in. This says W transpose X. This is just a way of looking. This is a different way of looking at a dot product between two vectors, right? Plus B. And I think you covered dot products before. Dot products are super important in all of machine learning, at least deep learning, right? So now we've been able to create a function with respect to our parameter variables. That's what this function is. This function is also called MSE, or mean squared error. There are other loss functions or cost functions that are good at different kinds of things, right? And so that's what that's all about. Okay, I need to hurry up. All right, so just a little refresher. The model is the function shape we construct. For us, our model is basically X, yields, let's see, let me delete this to be precise with my things. X yields W, again, let me be precise. X dot X and Y. Sorry, geez, why am I having issues? Dot of the W plus the X, right? And that will tell us, if it's greater than 0, we guess top. If it's less than 0, we guess bottom. The loss or cost functions are functions that tell us how bad we are at it, right? And so we want it to be 0. Now, the optimizer is a method for reducing how bad we are at predicting. How do we do that? I will show you. So, reminder, this is the actual function. Notice that there is this square thing here. So we're going to make this we're going to munge this all together into a single variable. So it kind of looks like this, right? If you think, remember back in the day, x squared is like this parabola, right? And we want to find an x such that this is minimized. And everyone knows, like, this is minimized at the value 0. The question from Japreeti is, why do we square anyways? That's a good question. It's because it makes the answer super easy to find, right? We could do not square it, but then the math doesn't make it easy like this, right? It doesn't make it easy. Oh, I went too far back. It makes it hard. Because it's harder to find the minimum, and this way is really simple. There's other loss functions, though, to be completely clear. I've showed you the mean squared error. Maybe there's a mean error function, but I'm sure that one's hard to optimize. Great question. These are awesome questions. So we want to be at 0. So pretend now that this is a 2D world that we have to walk across, and obviously, if we're in a 2D world that we're walking across, then we have to think of this guy. Imagine you're a blind Mario guy, and you're standing here. Let me change the color here to something other than red. So we'll do green. Imagine you're standing at this point, and you want to know, and you're blind, and you want to know, which way do I go to get to the minimum? Do I go this way? Or do I go that way? What's the hammer that's going to tell us to go the right way? So I'm closing my eyes to think about it. So basically, think of Mario, little 2D Mario, like putting his toe forward and putting his toe back and measuring the slope. They never played Mario in India. You should. It's really fun. But it's basically a 2D scrolling game. So imagine Mario putting his toe forward and his toe back and looking at the slope. And wherever there is a negative slope, you want to go that way. So think of it like this. He puts his little toe forward just a tiny bit. He puts his little toe back just a tiny bit. And what we'll do is we'll divide these things, dy by dx, right? And then what we'll do is we'll take the limit, right? As the distance, as these things go to infinitely small. And now all of a sudden you're looking at calculus and derivatives, right? So the derivative at any point tells us the slope. And Mario, armed with that knowledge, armed with that knowledge, is able to make decisions about which way to walk. So I'll just tell you, the derivative of x squared is 2x. And I this is so dumb because I think I'm 2 years old. So the way I remember polynomial derivatives is that these guys move over, and then these guys get so sad that we subtract one off. And so basically, that's a derivative. Derivative of x squared is 2x. And so let's take a look at it. Let's go to point number 3. We're at 3 on this x squared. This is minus 3. Mario is a genius only because he's armed with the derivative power of calculus. So let's take a look. The function value of x squared at 3 is 9, right? It's 9 over here as well. The derivative at x equals 3, though, right, is 2x. So 2 times 3, the derivative of x equals of x squared, the derivative of x squared at 3 is 6, right? So we know that the slope is 6, and we know that we need to go in the negative direction. So let's subtract the derivative. So 3 minus 6 puts us all the way at minus 3. Boom. We overshot. That's okay. Mario can take again at x equals minus 3. The derivative of this function at minus 3 is minus 6, right? So we can say, great, Mario, walk in the direction of the negative derivative. And now all of a sudden we're at 3 again. Oopsies. He'll bounce back and forth. So what we do is we take, in order to find the minimum, in a stepwise way. Now, obviously, this is a closed form solution, and I'm looking at iterative ways of solving this because it's a dumb problem. But basically what we're doing is we're looking at the value of x, right? So this is x, x1 or the next one is equal to the value of x0 where it currently is, and we're subtracting the derivative of x squared at that point. But this is causing us to bounce back and forth. So what we do is we're going to subtract off a scaled version of this particular function at that point, and then we're going to assign it to 1. I don't like saying equals because I'm being mathematics, so we're going to say assign to this way. This scaled version, for example, if we put 1/2 and we're at 3, it puts us right at the 0 point, and we know that we've minimized the value of this function. So what you've just seen is an iterative approach to solving the minimization problem of a function, and this is called gradient descent. This alpha that we're using is called the learning rate. And what we're going to do is we're going to take the derivative with respect to the parameters w and b of the cost function. Well, no, sorry, this is a lie. With respect to w of the w, and this will give us the actual updated w. To be precise, this is actually not a. Why is my? Okay, let me go over here. Use my pen again. Okay. To be precise, it's not the derivative, it's the gradient, because we're working in multiple dimensions. So we take the gradient of the cost function, we scale it, we subtract off these values for the w. For those that are wondering, you remember the I didn't write it down, but it's 1 over n sum, you recall, of n over w transpose x plus b minus y quantity squared. Right, and then remember the derivative is this one feels so sad that it moves over and it subtracts 1, and then we multiply times the derivative of what's inside, right? So if we do that, step number 1, we move the 2 over, which we've done. We leave this because remember that the derivative of f of g of x, right? The derivative of this is the derivative of f of g of x times the derivative of g of x, right? And we're differentiating with respect to the parameter w, and so we take the 2 over here, and then we take the derivative of what's on the inside, and what's left is the x, right? And so you can see that here. This is the actual derivative, right? And we're going to use this value. And then next, the derivative of the b with respect to w, and this is a little bit easier. Remember 1 over n, we have w transpose x plus b minus y quantity squared. We take the 2 out in front for the derivative of the first one, so that's 2 over n sum, right, w transpose x plus b minus y, times the derivative of what's on the inside, which is with respect to b, and there's nothing there, so it's times 1. Right, and that's what we get here. Do you see that? Hopefully, you. If you're lost, it's okay. Basically, I've shown you the way to take the derivative of these functions. If you've looked at the previous mathy classes, Japriti, do I need to know so much detail? No, you do not. But AI 42 is all about you knowing exactly how it works. At least that's what Eva told me. So that's what I'm doing. All right. So the question you might have is, really? The answer is yes. Here is the simple thing. I'm going to shift enter this one. This is the thing that generates, this is just going to generate a bunch of those 9 square things for us. That's what this is doing. And again, look, I'm not using anything other than NumPy. I'm not even using, I'm just straight vanilla. Like you can see, I'm literally using nothing, and I'm using this only to show pictures. This is the function that will draw them for us. Wow. So let me, oops, Control Z. I deleted something. Let me draw a couple of them. I don't know. So let's see, draw, and then let's do generate. I don't know. Let's generate 120 of them, so you can see that we're making these pictures here. You see that? We just made a bunch of these pictures. If I were to do it again, they'd all be different because again, they're doing it randomly. You can see over there we are. Like I'm randomly creating pixel pictures, and you can see that that's darker at the top, it's a 1. It's darker at the bottom, it's a -1. We're just making these things. Perfect. So now look at this. Like I'm literally gonna just do exactly what I told you, right? All of this, it would fit on one screen. It does actually. So we'll start with a W. We'll just pick a random W. Yeah, we do have a variable explorer. It's right here, but I haven't made any yet. So great question. And then what we're going to do is we're generating more pictures. I'm going to divide by 255, so the values are between 0 and 1. And then I just reshape stuff. Here's the model function. Remember, h is x dot w. The loss function, remember, is h minus y, quantity squared, mean, right? It was 1 over n sum, right? H of x minus y, quantity squared. You see that? It's all right there. Now, the accuracy is different. How accurate are we? So what we're doing is we're getting the sign of h, and we're going to see if it equals y, and we're going to take the mean, because we're doing a bunch of these at a time, right? We're not just doing one at a time. We're getting a batch of them. So we're looking at maybe like, how many pictures are we looking at a time? Looks like we're looking at 512 pictures at a time, because we can put it all in matrix form. It likes that. Now what we're going to do is we're going to say if the accuracy is 1, stop doing work. Now let's look at the update, right? It's what we had before, right? 2 times x transpose dot h minus y. Now, let me go back to my slide so you can see it. Let's go back. W transpose x plus b minus y times x. So let's go back to this thing. And you can see that I simplified it because I just put the x in here. But it's exactly the same thing. Now, we need to keep doing this over and over and over again until, obviously, because remember, Mario is marching around. The question is, how do you know how many epochs there happen? You use data science, which is you guess and you check. I basically said 50,000, but you're going to see it's going to take a lot less. Boom. All right. So what we're going to do is we're going to train it. It took 2,076 tries, and look at the answer that it came up with. Ones, almost zeros, minus ones. What? So that genius answer that you had in your head, it figured it out too in 2,076 steps. And just to be clear, let's get the calculator out here. 2,076 steps times 512 examples. It needed 1 million examples of 9 squares to come up with this. Yeah. I know this is anticlimactic, but after 2,000 tries, it figured out exactly. And I could keep it. I could make it go for a long time too. And this loss, remember the loss is the mean squared error. The other thing that we're doing is instead of looking at one picture at a time, we're looking at n pictures at a time. This is called a batch, right? And because we're using batches that are supposed to be drawn uniformly at random, so to speak, from the sample space, this is called SGD, or stochastic gradient descent. Yeah, so the question is, do we run a for loop behind the scenes? Yes, this is the for loop, the number of epochs. It generates more pictures. It does the model function, computes the loss, finds the accuracy, does the update with the derivative thing that we had before. Right, there's the gradient, and notice that we're subtracting off the gradient scaled by the learning rate. So exactly everything we did before. All right. Good. We did it. Now you're like, but Seth, what if we want to guess top, middle, or bottom? How do we do that? Genius. Well, we just make 3 of them. And then we get this big vector, this big matrix W instead of a vector W. Japriti, do we not need to fit in our model? We did. The thing is, we did. This is fitting. This is fitting right now. Except I'm doing it by hand using strictly calculus. So when you say model.fit, this is what it's doing behind the scenes. But again, we want people to know first principles. Okay. So now if we want to do top, middle, bottom, notice that if we take this vector and this matrix, yeah, it's all from scratch. Take that X vector. If you want to do a matrix vector dot product, I just think of the Cooking Monster because I'm an idiot. So basically grab that X, turn it on its side, and go num 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 dot product 3 times. Right? Notice that what we're doing is when we multiply these things times the top one dot product, it clears everything out and it just adds these things. Same thing here, adds these ones. Same thing here. And now all we do is we get the max index, and that tells us which one's the biggest one. And now again, the same thing. We do this, it tells us top, middle, bottom. It still works. This time I'm going to do predictions. So let's go to the triple one here. Again, nothing fancy, right? This here generates these things for us. So let me show you what this looks like. Now y, instead of the right answer, instead of being a single value, is a vector, and this says that 1 is the top one is the biggest. So the max index of this would be 0, right? Which means the top one is the darkest. The max index of this one would be 2, which means the bottom is the darkest. The max index of this one would be 1, which is the middle one. Right? Do you see that? Here, I'll draw some more of them so you can see them. These are all it just invents them, these pictures. But now we have a multi-value because we want to do 3 things. And notice though that this really did not change at all. That's the beauty of linear algebra. Except now what we're going to do is we're going to try to add the b. It's useless in this case, but we're going to add it so you can see it. So we're going to start with a random weight vector, a W, a random bias, B. Right? You can see there's my learning rate, 1, 1 time 10 to the minus 2. Again here, there's the model, the loss, right? Same thing. This is going to be a little bit different, right? Because the accuracy is the argmax, you remember, and we take the mean of it. So argmax of y, remember y is going to be 1 minus 1 minus 1, and the argmax is going to be 0. So that's what this is. And if we get the right value in this, it's going to, you know. And then the update is, I mean, it's the same thing. It's the same thing, except now, you know, this one doesn't have the x dot, right? Because that's the, we don't, with the derivative with respect to the bias. All right, so let's create this function for training, and then let's run it. Look at the matrix that it learned. All right, ones here, negative numbers here, basically zeros. Negative numbers here. Here, let me erase this because I want to be super emphatic about this. Ones here, ones here, ones here, and then you can see all these other numbers, basically zeros. And then the B, notice that these are all negligible numbers. In fact, we can take the B out. Let's just take it out. So let's take it out and see what happened. B is gone. B is gone here. B is gone here. We don't need this. Yeah, I think this does it. So I rebuilt this. Good. And now let's train it again. Notice that the B is just a residual from the last B. That's just there because it's just remembers it. But notice we don't get too much of a change because the B doesn't matter in this case. But we basically get ones, 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 and zeros everywhere else. So it learned this stuff on its own. Now let's do some predictions. Let me put the B's back, though, because I think my predict has a B. No, it actually doesn't matter. I could just take it out. But I'm just going to do this anyways because I don't want there to be an error. There we go. Done. And now when we want to do a prediction, notice that our function, let me change this to H, right? H. You know what? We could even, this is our function. I could make a function. We do lambda x equals, this is our thing. So we're going to say x dot with w and then plus b. And this is going to be a np dot array. Something like this. Maybe I'm not doing this right, but you get the point, right? It's basically, we can make a function out of this, right? And so notice that this is the input picture. We get the H, and then we do the argmax of A. And that tells us whether it's darker at the top or darker at the bottom. So let me change this to something completely obvious, right? And then this 13. It's going to be dark at the top, so we hope. Now let's change this to a 12. Still darker at the top. Let me put a 255 here. You see that? It's guessing middle. And now let's change this to a 12 and let's put like 255s here. You see that? Literally, like, honestly, this is how you do computer vision classification. I'll show you, like, this is basically it when it comes to that. It still works. This time we did a little bit of predictions. And basically to save the model, you just save the weight vector and the bias. And then you load it up, and then you use it to predict. All right, so let's do a little review because I'm out of time. We did artificial intelligence, machine learning. We talked about that. We did supervised learning in practice. We did the model loss function optimization method. We did the 9-square problem, and then single output problem, and then multiple output problem. For next time, we'll do more complex model functions. I'm a computer vision person, so we're going to do image classification. We're going to build on the basic perceptron, which is what you just saw. That's perceptron. That's the model that I built. But we're going to use it to create neural networks. We're going to understand a little bit about convolutions, and then we're going to add some depth to our neural networks, and then more complex loss functions. And we're going to do it all in PyTorch next time. So that's it. Any questions, friends? All right.
Wow, Seth, it was amazing. I really love that you made the whole thing from scratch, and I always love to watch this. This is just the best ever. We have a few questions quickly, and then I know you have to run away because you answered most of them. So just quickly, a few questions here. So first of all, whether the notebook that you showed us today available somewhere.
Yeah, so I'll check them in because I made some changes to it. If you go to let's see here, let me bring it up, github.com, Seth Juarez, and then I think it's deep learning with PyTorch. I think that's it.
I have it, I think, already. If this is the one,
I'll check in. I made some changes, but you can see there's some of that goodness here.
All right, and then another question. Which one should we take? Let's see. Okay, which one should we take?
I think we can take at least this one here. Oh, sorry.
Okay, so whether there is any book that you would recommend to learn all these?
It depends on if you're a top-down learner or a bottom-up learner. If you're a top-down learner where you just want to solve problems with deep learning, I would suggest anything from his name is escaping me. He's from Australia. He does there's an AI framework that he builds. I can't remember it, but shoot, I bought the book, so I'm gonna look on Amazon right now and remember the book. But yeah, queue up the next question so I can answer, because I bought the book. I'm just forgetting the name of it. I have it upstairs right next to my bed. It gives me comfort in times of
that's sounds interesting. Yes.
But looking here, I buy a lot of stuff on Amazon. Dang, like I'm already on page 4. Let me see.
In the meantime, I have a favorite question I want to ask from you, because I am interested in that actually as well. Okay. So what do you do beyond tech stuff?
So my job is to help every developer and data scientist and machine learning engineer be successful with AI in the cloud. And we do that by creating content, refining our products at Microsoft, and then growing community around them. Does that help?
I think so.
Yeah, that's what I do, but I do it with tech. So I'm trying to find, dang it, I'm not going to find it. There's a lot of good books, but I'm not finding it right now. There's a really cool framework, deep learning. Oh, Jeremy Howard, that's his name. Jeremy Howard. Howard. If you're doing top down. So Jeremy Howard does some really good books. So just look at those. The last one he came out with, let me see, Jeremy Howard. It's called Deep Learning for Coders with Fast AI and PyTorch. That's if you're doing top down. If you're doing bottom up, there's a brand new book that's actually free online called The Mathematics of Machine Learning. It's a pretty good one. And that's if you want to get in depth to it. I answered it.
Cool. Thank you. Yeah. Thank you a lot. And I'm also very, very thankful for the session. It was really awesome. I enjoyed it a lot, and I can surely say that the audience also enjoyed it very much. So we are very happy that you are here with us, and see you in 2 weeks.
2 weeks.
Back with deep learning stuff.
With PyTorch.
And I can't wait. So Thank you a lot for joining us, everyone. And please don't forget to come back in 2 weeks and talk about deep learning with Seth Juarez. So thank you a lot again today.
Thank you so much.